You gotta fight for your right to do statistics. All right, tribute to MCA there. Okay, then 5 is about the normal standard distribution. I realize I am not your normal standard math teacher, but still I'm going to try to teach you this stuff. All right, here are your questions that you're going to have to answer after the quiz. First thing we do in class on Thursday will be the quiz on 10.1 to 10.4, and truthfully, I think the hardest stuff is going to be the 10.2. I guess some of the same calculations happen in 10.3 where you do the binom PDF and then you have to add up part of a list and interpret that correctly. I'm not going to go too crazy on the 10.3 questions about hypotheses or really the 10.4 stuff about the equation of the actual standard normal distribution and how they did the algebraic transformations. I'm not going to ask you a lot of that stuff. Cool to know that. That really ties back really well with the end of semester 1, but it's not going to be on this quiz. Okay, so what is the 10.5 about? Okay, so you spent all this time getting familiar with, oh, I'm actually saying what I wrote there. I didn't really mean to do that. That's how I think of it. So let me not look at that. Let me actually just draw at you a bit instead of talk at you a bit. Okay, so they showed you this standard curve until you were sick of it. And it's the same one where this is the 0.39, this is the 0, this is the z-axis, and these little tick marks here kind of stand for standard deviations. And there's an inflection point at 1, above 1 and -1 is where the inflections are. The area under the whole thing is 1, of course, because it's a standard, it's a probability distribution. After we get to about 3 on the tail ends on both places, there's really no area to speak of. The area under this entire thing is approximately 1. So since it's a probability distribution, we can actually use it to calculate probabilities. You can find out it's kind of fun to color and talk at the same time. It's it's used for probability distributions. Oh, the block is over. And we can find out, whoa, how come that did that? Interesting. Oh, it stopped. We could find out, like, what's this little zone in here? Like, it might be really important for us to know, or we may be able to answer a question. What is the area of the curve between here? I don't really like that color. Doesn't show you what I'm talking about. Between 1 and 0. Like, I might really want to know what that area is. Actually, that's kind of a crazy one. Let's not start with that one. Let's start with from 1 on down. Okay, what kind of question is that good for? Well, it's not quite. We're not quite at this point yet. I'm kind of giving you a little hint at what 10.6 is about, because 10.6 is like the whole reason to have standard normal curves in real life, sort of. 10.5 is getting ready for that. 10.5 is still using the crazy standard normal distribution that hasn't been shifted around for real life at all yet. It's still just this weird thing. It's this version of it. It look like this times e to the negative x squared over 2. I can't believe I remembered all that stuff. I don't expect you to. This is actually what we're talking about in 10.5. In 10.6, we're going to move it around. The mean might not be at 0 anymore. The mean's probably going to be way less than 0. The mean will actually be like, some number we care about, like the mean average height of people who are your age or something like that, or the mean score on an actual SAT test. So we're gonna shift it around up and down, left and right a little bit, but it's all going to be congruent or similar to this sort of, I don't want to call it the parent. It's like, I don't know, the oldest child, I guess, of this family of functions. Then we start messing that up a little more for the next one. But anyway, for now, to get you ready for what's coming up, there would be a question where it will say, all right, what's the probability that if you threw a dart at this orange area, that's going to land to the left of a standard deviation of 1? And that is the type of reasoning you're going to have to use on this kind of thing. Or, what's the probability it lands between 2 and 3 in that little area there? How much of the total area is this area here? Well, this seems like a pretty crazy thing to try to figure out. But again, as I keep telling you, this curve is so popular, it's so worth knowing about, that your calculator is set up to handle just this exact thing. Let's try to figure this out. How much of the area of, the total distribution of this great big pile of area that's all adds up to 1, how much of it is below this particular point on the axis? I explain it here in the notes document about how you do this on the calculator. It's in the same distribution menu where we found binomial PDF, but we're actually going to use normal CDF here. Normal meaning we're using normal distribution instead of binomial, and CDF meaning we are actually going to add up a range of values all at once here. So let me show you on the calculator. Go to distribution. I want normal CDF. Thinking now, since that adds one up, maybe the binomial CDF would have helped in some of the questions like we did in 10.2, but I don't want to confuse you now. Okay, I like the way we did it. So, all right, normal CDF, there it is. It came from the distribution menu. There's the little key press history if you can't find that. Yeah, and what is it good for? What does it want? It wants lower bound z-score and upper bound z-score. And all it does is then is going to add up this area between whatever you give it as a, sort of a lower bound. Like I use my lower bound in my question here is kind of like negative infinity. That's a bit of a problem. We're gonna worry about that in a second. I'm gonna add up all these values all the way up here to upper bound. My upper bound is easy to figure out. My upper bound is it's a bound. My upper bound is actually just going to be 1 because that's where I want to stop. I want to add up all it asks for where's the interval on the z axis, sort of like between where and where do you want me to add up the area? Well, I want it to add up from negative infinity all the way up to positive 1. Negative infinity, if you remember from the last section, 10.4, we first started talking about this area. After about -3, there really isn't a whole lot of area out here. Yes, it's infinitely long, but this asymptote starts to get closer and closer. I mean, this graph starts to get closer and closer to the asymptote. We don't really care about it. The book says if you actually started adding this around -5, it's pretty much the same as if you entered it at negative infinity. 99.9% of the area is between -3 and +3. So -5 to +5 should give you all of it, or at least rounded on the calculator. If you feel nervous about that, go to -10. It'll add another tiny little fraction. You get a little more exact. But 5 standard deviations either way is sort of past the point of caring, according to our book. But you know what? I care a little more than that. I'm going to go all the way up to -10, just because, going the extra mile for you guys. Okay, so from -10 up to 1 is where I stop. And that's it. It was basically saying, give me all the area under the normal curve between -10 and 1. And it turns out to be about 84%. Does that seem reasonable? Did I have about 84% of the area here? Well, I just drew this by hand. But yeah, I mean, this would be 50, correct? Because we have a symmetrical halves here, so that's 50. You'll get real familiar with how much area is in each one of these little banks from 0 to 1 and 1 to 2 and 2 to 3. You'll find out pretty soon that there's between 30 and 40% area here, between 30 and 40% area here. So yeah, this is kind of over 80. I got 50 down here and then plus another 30 something. So yeah, that turns out to be 84%. And if you didn't believe me on the -10, -5 thing, if I did this again, instead of -10, if I went -5, it's not going to be a whole lot different. From -5 up to 1, it's a little different. I mean, once you get down here to like the 6th decimal place, it is a little bit different. There's a little more area there down there past -5, but it's pretty insignificant. So -10 doesn't take that long. -9 is as many button pushes as -5, and we're accurate to like 6 or 7 decimal places already, so that's fine. Okay. And notice I was asking for lower bound and upper bound. It's not always that one of your bounds is going to be infinity. There'll be lots of times on your graph where you're going to have to find just part of it. Like there's a lot of them where it'll ask you to calculate something like, let's find all the area between here and here. Like, I don't know why you'd want to know that exact area, but let's say between 0.8 standard deviations and 1.2 standard deviations. Like how many people are falling in that little zone. Like say you have some kind of, you have your school of kids who took the AP Psych exam this past Monday, and let's say the whole school has a bunch of kids that fall in this area that's around 1 standard deviations above the mean. We want to know how rare is it for all of us to fall in there, or something. So I would have to manipulate this, of course, in the 10/6 sense, where the average here wouldn't be 0, but whatever I need. But it will always come back to this, like what fraction of the entire orange area is in this little red zone. So I just do that little thing again. I'd say I want the normal, now I can just do enter, it's kind of nice. The normal curve area between a positive value of 0.8 and 1.2. Not 12, 1.2. Let me go back and hit the decimal point. Thank you very much. between 0.8 and 1.2 is almost 10%. So that kind of tells you what's going on. About 10% of the entire population is in that zone. There's one little weird thing that comes up in here, and they're talking about what if you had to compute probabilities for something that was discrete, like binomial probabilities. And we had that one that was what if you had exactly 8 tosses out of 10, or sorry, 8 out of 16 on your coin toss that was heads and all that kind of stuff. And you have these binomial probability distributions that are not really normal curves, but they're a little bit different. And one standard deviation was, oh, this looks pretty good actually. This stood for like 8 heads, and this stood for 10 heads, and this stood for 6 heads. We knew that one standard deviation was two-way. How do I actually calculate the area of this zone in here for like one? Wait, this is supposed to be 2 standard deviations away. Anyway, easily fixed. Let's just change our scale. You have a normal curve compared to a binomial thing, and it doesn't quite line up. Like if I want to know exactly what this probability is, I can't just find the probability of exactly 9 as an interval. 9 is just this point right here. If I was going to readjust this z-score, so let me get this axis out of the way, because now this, oh really? That whole thing moves together? I didn't want that to happen. All right, so let's yeah, this median would be 8. I can't really just calculate the probability of 9 happening by itself, because this normal distribution thing always wants an interval of a whole bunch of points. So if I know that there's one occurrence in that area, I should set my sort of bin width like a histogram. I should set my interval width to be 1, where the only one occurrence in that zone is the one I care about. So if this was really 1 standard deviation, I'd set it from like 0.5 standard deviations to, let's say, equals, implies that z equals 1. I'd set that from a 0.5 to a 1.5 or something. If I knew that there was only one possibility in there, and I wanted to calculate it for a width of sort of one possibility, I would calculate everything in between a half and 1.5. Even though that doesn't make sense for coin tosses, you can't have a half of a head or 1.5 heads. You can only have exactly that one number of heads. But this is how you make that adjustment. I don't know why they talk about this in 10.5. It makes a whole lot more sense to talk about this in 10.6. So don't worry about that for now. But in one of the sort of adjustments for how to make this smooth curve behave like rectangles, you just have to divide it into the correct width of rectangle, and then you can find that area. Just looking here at the other examples they have in the book for areas they ask you to calculate. They do ask you to calculate some, they say above, and the way they talk about it in the book, it's like they want you to look at this cumbersome old-fashioned table of these values, but you have this all in your calculator. So if you wanted to just find the value above a certain point, you'd enter the lower point in your as your lower bound, and then you just enter like something like 5 or 10 in your upper bound. If you wanted to find all the stuff above here, you just say, well, calculate this area from 2 to 10 or something. It would give you all that area. In the book, they have the table. It only gives values below, so if you want above, you have to figure this out and subtract from 1. I mean, it's kind of a big disaster. Your book doesn't plan on you necessarily having a TI-84, which you do, which helps a lot. Okay, well, I think that's it. Notice, yeah, in 10.6, I'm sort of hinting that eventually you're going to be able to change the mean and standard deviation of one of those curves to get it to model the data you really care about. Or you can change the data you really care about to be something that can actually be approximated with the normal standard curve in standard position, sort of. Anyway, good luck on the quiz. I will see you on Thursday.